Okay, let's dive right into this and explore the fascinating illusion of how modern cloud infrastructure handles massive traffic spikes effortlessly. In this explainer, we're going to completely pull back the curtain on the magic behind horizontal autoscaling, which is absolutely one of the most powerful and, frankly, most critical features of modern application deployment.
Think about the ultimate magic trick in the tech world for a second. You have a website, and it manages to stay perfectly online while thousands, maybe tens of thousands of users flood in at exactly the same time. How does that actually happen? I mean, in the past, this scenario meant almost certain doom. Picture the sheer panic of engineers waking up to pager alerts at 3 a.m., scrambling to figure out why users are just staring at massive 503 error screens. Servers would literally crash into the sudden wait, databases would lock up, and revenue would just evaporate by the minute. But today, a well-architected system just effortlessly adapts to that same tidal wave of traffic.
To understand how, we have to look at the old struggle of making one machine bigger versus the Kubernetes way. In the past, we relied almost entirely on vertical scaling. If your app was struggling, you just made that one single server bigger. You'd throw more CPU at it, buy more memory, and kind of just pray it holds. But that strategy has strict physical limits. You can only buy so much RAM before you literally hit a wall. The true magic of Kubernetes is horizontal scaling. Instead of making one machine impossibly huge and expensive, we simply add more identical, smaller units, called pods. It's an infinitely more flexible, dynamic way to handle unpredictable load. Which brings us to our first section, the scaling problem and the magic of HPA.
See, without autoscaling, we really only have two bad options. Either our app crashes because we didn't anticipate the traffic, or we pay an absolute fortune to our cloud provider to keep a massive farm of servers running 24/7 just in case a spike happens. Neither of those is sustainable, right? So Kubernetes uses a completely declarative approach. You don't write imperative scripts commanding the system to add a pod right now. Instead, you simply declare your desired state. It's exactly like setting a thermostat in your house. You say, hey, I want my application to always have enough resources to handle the current load, and the underlying controllers do the heavy lifting to make that a reality. It's a beautifully intelligent, self-healing system.
And our main magician for this trick is the Horizontal Pod Autoscaler, or HPA for short. The HPA is a dedicated Kubernetes controller, and its sole job in life is to automatically scale the number of your pod replicas up or down based on specific metrics, like how hard the CPUs are working across your entire application. The HPA is a core resource in the Kubernetes ecosystem. It sits right alongside the deployments and replica sets it manages. Think of it as an automated brain, constantly observing your deployment workloads, analyzing their stress levels, and making split-second decisions without requiring any human intervention whatsoever. So the crucial point is this three-step mechanical process that pulls back the curtain on the whole trick. It's actually very logical. Step 1. The system obtains metrics from the running pods. Step 2. It calculates exactly how many pods are required to handle that load. And Step 3. It executes by updating the official replica count. Let's walk through exactly how each of these works in practice. Starting with Step 1, gathering metrics. Let's trace the journey of a single metric. It's important to realize that autoscaling isn't magic teleportation. It obeys the laws of physics and time. First, in a matter of milliseconds, the application container generates a metric. Next, inside every node in your cluster, an agent called cAdvisor is constantly collecting these metrics from the containers running there, aggregating them over a period of seconds. Then, those metrics get aggregated cluster-wide by a component called Heapster, which can take minutes. Finally, the HPA periodically queries this aggregated data through REST calls to get the full picture. Because this data has to travel through these different layers, there is a natural delay. The system literally needs a moment to perceive the traffic spike. Interestingly, there's been an evolution here. While earlier versions of Kubernetes relied directly on Heapster, newer versions shifted to obtaining these metrics through an aggregated version of the Resource Metrics API directly. This makes the collection process even more robust, faster, and integrated natively right into the Kubernetes API server itself. Now, while checking CPU usage is for sure the most common way to trigger scaling, the HPA is incredibly flexible. You can scale based on resource metrics like raw CPU or memory. But you can also scale based on pods metrics, like how many queries per second a specific pod is handling. You can even scale based on object metrics, meaning the HPA watches an entirely different object altogether. For example, if your checkout page starts taking 3 seconds to load, triggering high request latency on your main web ingress, the HPA can watch that latency metric and instantly scale up your backend pods to process those checkouts faster.
Okay, on to step 2, doing the math.
Let's set a baseline. Imagine we configure our HPA with a target CPU utilization of 30%. Think of this target value just like that thermostat setting we talked about, but for your app's processing power. We are explicitly telling the system, hey, I want the average CPU usage across all my pods to hover right around 30%.
Suddenly, boom, a massive traffic spike hits. We only have one pod running, and its CPU usage shoots up to an overwhelming 108%. The autoscaler steps in and does some surprisingly satisfying math. It takes the current load of 108%, divides it by our target of 30%, which equals 3.6. Since we obviously can't have a fraction of a pod, it rounds up. The system instantly knows it needs exactly 4 pods to restore perfect balance.
And look at the immediate result. When those 3 new pods spin up, there are now 4 pods sharing that 108% total load. 108 divided by 4 gives us an average CPU utilization of 27% across the board. That is perfectly cozily close to our 30% target. The magic trick worked flawlessly, and your app didn't even flinch.
But the system is also smart enough not to panic. Notice the strict cooldown periods enforced by the system. If traffic is wildly fluctuating second by second, we don't want the cluster violently spinning pods up and destroying them right after. That creates a really dangerous condition known as thrashing, where the system spends more computing energy creating and destroying pods than actually serving users. To prevent this chaos, Kubernetes dictates it'll only scale up if no rescaling has happened in the last 3 minutes, and it limits how many pods it adds at once, usually doubling the current amount. Scaling down happens even more cautiously, with a 5-minute cooldown, ensuring the traffic spike is truly, absolutely over before pulling capacity.
Which takes us to step 3, the execution. What's amazing here is the beauty of abstraction. The HPA itself doesn't actually create the individual pods. It simply updates a single number, the replicas field, on the target resource, like a deployment or a ReplicaSet, using something called the scale subresource. That's it. It's a tiny, incredibly lightweight API endpoint, which is why it's so incredibly fast. The HPA just changes a number on a virtual chalkboard, and the ReplicaSet controller sees that new number and physically goes out to spin up the new pods. But wait. This introduces a massive cliffhanger. We've been talking entirely about virtual pods so far. What happens when your physical server, the actual hardware node sitting in a data center, simply has no more memory or CPU left to give? The HPA can demand 100 new pods all at once, but if the physical metal is tapped out, the pods will just sit there in a pending state, completely helpless, unable to run. We have to evolve our narrative from scaling virtual pods to scaling the actual underlying physical infrastructure. Let's look at scaling the physical nodes. This is exactly where the cluster autoscaler comes into play. If the HPA is the magician for your application, the cluster autoscaler is the magician for your underlying infrastructure. When it notices that new pods cannot be scheduled because the existing nodes are completely full, it literally reaches out to your cloud provider like AWS or Google Cloud and asks it to boot up brand new, real, physical silicon servers and attach them to your cluster. It automatically bridges the gap between software and hardware. And just like the HPA, the cluster autoscaler is incredibly frugal. It actively monitors your physical nodes to ensure you aren't paying for hardware you aren't using. If a node's CPU and memory requests drop below 50%, and it ensures that any running pods can be safely moved to other servers, it will gracefully evacuate that node and shut the physical server down. It's an intelligent cleanup crew, saving you money automatically. Now, moving pods around to shut down a physical server could be dangerous if not handled right. That's why Kubernetes provides a safety net called the pod disruption budget. You can think of it exactly like budgeting how much downtime you are willing to tolerate. This simple configuration guarantees that during these physical hardware shuffle events, Kubernetes will never evict so many pods that your app goes offline. It ensures a minimum number of pods are always serving traffic, making sweeping infrastructure changes completely invisible to your end users. From the virtual pods spinning up in seconds, to the physical cloud servers being summoned into existence, the mechanical magic of Kubernetes autoscaling is truly a marvel. It transforms unpredictable chaos into a smooth, calculated response. So, looking at your own applications in the cloud, how will you set your target metrics to handle your next big traffic spike?